Hi everyone, my name is Vikram and I'm going to present about using TPM for Zen on the ARM. So let's talk briefly about like what is TPM and why it's useful. So TPM is basically a specialized chip on your laptop or on your desktop computers, even on modern servers or phones and stuff, which is basically designed to secure the hardware with integrated cryptographic keys and tasks. So this this chip basically stores a variety of sensitive information like user credentials, password, fingerprint, and encryption keys and stuff. And it stores in a basically a hardware which is like safe from external attack. How TPM work, like when your system boots up, like laptop or your desktop boots up, TPM basically authenticates it, and then TPM also provides an cryptographic key to unlock the encrypted driver. And if the key is validated, then your computer is going to boot as normal. If not, it won't start. Now, this encryption and decryption of information via TPM has a significant advantage by doing it by just like your software, because the keys are tied to an external hardware, and that is TPM specifications are basically maintained by Trusted Computing Group, which is basically a group of like 140 plus companies which decides the open source standard for the TPM. TPM is like widely used nowadays, and it's been around for almost 20 years. The latest version of TPM is TPM 2.0 CRB, which was introduced in 2016. Most of the common OSs like Windows, Linux has this support for the TPM. Let's talk a little bit more into like the components of the TPM. Main component I'm going to talk about is non-volatile storage and secure PCRs, which is PC registers. So non-volatile storage basically store the persistent state of the TPM, and it stores like endorsement keys and owner password and stuff. It also store information about storage root keys. Storage root keys is basically when the TPM is initially configured, it generates the storage root key. Endorsement key, which is like quite used in the TPM, and it's very specific to each TPM chip, and it's fixed when the TPM is manufactured, so it cannot be changed and it's not visible outside the TPM. Next, about the secure PCR, which is like a volatile state storage, and the PCR are basically the hash operation capable registers. These are used to basically measure the system state, like if you want to do the secure boot and secure boot. So example like for example, like when the boot happens, BL2 basically can measure itself, and it can also measure the next hardware start sequence like BL31, BL32, Linux and stuff. And this effectively creates a chain of trust, which basically guarantees that the system that we are booting or the system is verified. Another part is the cryptographic processor, which is basically contains different engines to create SHA, RSAs and stuff. So in the context of Zen, because the TPM can basically provide a security to each operating system, and Zen hypervisor basically maintain multiple keys, so it can be quite useful for Zen. For the ARM architecture right now, the support is not there, so only hardware TPM which is available, and there's one of them on each system. So only one guest can basically access the hardware TPM. Again, we want to share it with other guests. We can just remap it, but how do we extend or how do we enable each guest to have its own TPM? So we went with a emulated TPM, like we have used basically QEMU software TPM and Zen to basically enable emulated TPM for each TPMs. We are going to talk a little bit about this in the next slide, but for the virtual TPM, like Zen x86 already has support, but it's not completely up to date for VTPM 2.0. It's basically 1.0, which is an old standard, and it has dependency on OS, which like it uses for the front end and back end drivers, which is going to be another problem for the ARM architecture because we are not aware of the mini OS infrastructure exists for the ARM. So as we talked on the last slide, that x86 already has the PVVTM. Can we use that? We went basically through the implementation, and it turned out like it's going to require a lot of work or efforts to basically enable the TPM for ARM. And so we went with another approach, which is basically using the QEMU with software TPM. QEMU has the support for 1.2 and 2.0, and QEMU also support basically creating the IOREQ servers for the Zen hypervisor. So I'm going to talk a little bit about the software TPMs. So software TPM is basically TPM software emulation. It's an open source project. Has basically support for TPM 1.2 and V2, and it supports TPM functionalities over sockets, character devices, and Linux interfaces. For the QEMU, it can work over a Unix socket. And here's a link for the software TPM project. So we have talked about like to enable TPM for Zen on the ARM, we are going to need like software TPM is one component, and the QEMU is going to be another one. So for if we talk about the QEMU, right now it supports both the 1.2 and 2.0 emulators. It provides basically a front end and a back end in the QEMU. So back end connects to the software TPM, which is emulates the TPM, and the front end we can just like use it as an interface towards the guest. For the QEMU Zen, it already has the IR Zen PV machine is available, but it does not have IOREQ enabled. So that's also a bit of so what are the like updates that we did in the QEMU to work with the software TPM? So first thing is that we basically change QEMU in a way that we can use the common functionalities of Zen even for the ARM machines. Then what we did was that we created a small Zen PV machine for the ARM, and the machine as of now it's like very lightweight, and it does like just a few things: create the IOREQ server and register it with the Zen hypervisor, and it also adds the TPM emulator, and it inside the QEMU it contains basically TPM-TIS device also, where the MMIOs and and stuff are mapped. And lastly, for the update in Zen tools, basically for the ARM, when we are going to create a new DomU or a new guest, what we did was that we added a new config option, which is TPM equals to 1. So what this is going to do is that when it starts the QEMU Zen PV, it's just going to append a few extra arguments QEMU so that it can connect to the software TPM. So here is like a basically block diagram to understand the flow better. So inside the Zen hypervisor, we have like DOM0, and inside DOM0, we are going to run the software TPM. And also, when we're going to create a new DomU, what's going to happen is that Zen is going to invoke the QEMU, and QEMU is going to start a IOREQ server. The IOREQ server is going to register with the Zen hypervisor, and the TPM-TIS device inside the QEMU, it's basically start the front end and back end. The back end is going to connect to the TPM. So when DomU starts to boot, and if the kernel in the DomU has the TPM driver enabled, so the TPM driver is going to request for the MMIO access, and the access has to basically go to the Zen IOREQ, and from Zen IOREQ it will be from QEMU, it will be sent to as per the MMIO access, it's going to redirect it to here are like the basic commands to work. So to start this software TPM, all we need is that we need software TPM application, and we just need to create a common directory, and we need to define the type of sockets and stuff that we want to initiate. For DomU, see the config file, it looks pretty standard, like we are mentioning information about kernel, RAM disk. It's the only extra option is TPM equal to, and that's going to generate the required arguments for. So Avi, is there a way for me to play this video?
Yeah, cool. Hello. Unfortunately,
Hi.
videos, we can't see the videos because I think you have to upload it first, like on YouTube, and then fetch it from this thing. Yeah,
Oh, I see.
we heard about that just today.
Okay,
So,
no worries. So in the video, like in the demo, it's just like the demo was just trying to show the same thing, like we're inside DOM0, and we were initiating a new DOM2, and we were seeing the like software TPM. We just enabled logs and stuff just to see what data and what encryption information DomU driver was sending when it was initiating, and then we were also running a user level application which does the basic PCR. The next one. So about like overview of the thing that TPM for Zen on the ARM is basically fully emulated, which enables each guest to get its own unique TPM. It works exactly the same way that if a user has to basically use an hardware TPM guest, of course, it has like dependency on QEMU and software TPM, and both needs to run DOM0, so that's going to be a problem for DOM0 less. So that's the current status of things for TPM on ARM. Yeah, I just wanted to thank my teammate Stefano and Ian for brainstorming and helping on implementing this. For the future work, now that we have a ZenPV machine on the ARM and it has basic support for IOREQ and it has support for emulating different devices, one of the future work can be VirtIO enablement or any other emulated device that can be useful for the Zen. For the VirtIO enablement, I would say Oleg Center already did some work on this ZenPV ARM machine that we have created, and he was able to test like basic things for the IO. And next phase of the work would be like how to figure out and how to enable it for DOM0 less.
Any questions? Okay. I have a question about managing those SWTPM instances. It needs some persistent data to store those secrets. How is it going to be managed?
Yeah. So you ask about software TPM is going to store the persistent states and how it's going to be managed.
Yes.
So
example, it was just a temporary directory, but I'm wondering how is it going to work?
So about software TPM, let me answer from my understanding. Again, I'm not an expert on that part, but I feel that the software TPM basically stores these information temporarily over a path, basically, and so the basic softwares or in the users in DOM0 can still have basically peek to those files, but it's going to store these things in DOM0. Another way is that for the x86 Zen, where they uses the hardware to store a few of the sensitive information, we are yet to basically add that option, and don't know like how we are going to access the hardware till then.
Another question is XL2 stack is going to also start this SWTPM instances, or it needs to be done separately?
Right now, it's need to be done separately. So that's like we were just like done with the basic flow of the enabling TPM. So we have some work to do, but right now it's just like you need to start software TPM separately and then you XL2.
It basically communicates on a socket. So there is a socket that you start software TPM instance separately. It opens a socket communication, and then from this Zen, the IOREQ server, it's going to talk to that socket. So like that.
Yeah, I used SWTPM and maintaining those instances manually, which I did was really messy. So I'm wondering, is Excel going to support that internally, or is this need to be done separately still?
I think it's
right now, right now it's going to be separate. But yeah, for the next step, probably we can try to find like if this can be managed from Excel only.
Thanks.
I have one question. Maybe do you know if currently on x86 architecture there's some implementation of VTPM and how it's differ from what you did on ARM platform? Which is the main difference? Because I don't see which parts are different from two platforms.
So for the x86, the only two different thing is that x86 still has 1.2 TPM, which is quite old, and another one is that in the implementation of x86, it uses the mini OS, and I'm not sure if like ARM for mini OS is basically officially supported for the ARM.
So mainly we found that in Linux, the software TPM drivers are supported. And that could talk to our software TPM instances, and it needs to be on TPM 2.0.
Yeah, okay. Any other questions? Okay, thank you.
Thank you.